Good morning. Good morning. So apologies for the slight delay in the start because of some technical glitch, which we have almost resolved. So we approach almost the last phase of this lecture series now. This is the penultimate lecture. In fact, this is the last lecture in terms of all the conventional topics that we are going to cover. And tomorrow's one is more on advanced topics and research on vibration control related to it. But also other controls like pitch control will be discussed a bit more in detail. Um, so I assume you don't have much difficulty in reading the screen, obviously, because there's a bit of patch of corner being problem. Anyway, you have soft copies and hard copies. Well, so the topic of today's lecture is on offshore wind turbine, which is really the direction in which the wind turbine technology is moving towards. It's relatively unknown in terms of available knowledge, how wind turbines behave, how they interact with the wind and wave. And as you know, in offshore wind turbines, it's not just the aerodynamics. Now we're talking about, but we are also concerned with hydrodynamics. So the wave loading, current loading, the foundation systems are very different. It's no longer a foundation because we're talking about floating wind turbines. Then it is really a platform which is supported by cables. So you now have flexible mooring cables. So like oil platforms and so on. So you don't have the classical geotechniques anymore, but you have hydrodynamics, you have offshore engineering, you have current loading, and obviously the interaction with the wind, wave, and current poses challenges. And in particular, because as we move in the field of hydrodynamics, though it is a very classical area in the sense that has been studied over a century now, because hydraulics used to be called the classical in many sense, and then obviously people were doing fluid mechanics in the sense of nonlinear waves in the mathematical field also did hydrodynamics. And nonlinear water waves, actually together, nonlinear hydrodynamics is a challenging field. And there are so many open questions still to be resolved. And in fact, as Richard Feynman said, that water waves obviously is a nonlinear wave, and it actually is the most complex of all waves that we see around us. That's starting from light, like electromagnetic wave field, acoustic waves, other telecommunication waves, all the complicated features which exist in these waves are present in water wave. So water wave is the most challenging scientific discipline if you want to classify in terms of the hard problems to solve. And to give you some example, one example is, for example, or one example is the Stokes wave, which was conjectured by Stokes in 1867, and only the existence has been proved the last 12 years. So that kind of challenge. Also, wave breaking is another area, and wave why it breaks, how it breaks is not unknown, not known actually, still unknown. And it was known that laminar flow then proceeds to waves of small amplitude. That's where the linear wave theory comes in. It's better understood. But it can develop rogue waves, for example, meaning that waves of very high amplitude or sharp gradients. And these are present not just in water waves, but also, for example, in nonlinear optics as well. Similarly, Scott Russell, sometime in 1870s, I think, also observed single waves or humps of water moving at a speed of the fast decay in the shape. And these are called solitary waves, actually. And solitary waves also have a special type of wave called solitons. And soliton is the fundamental of, for example, communication. Also, it has some connection with neural wave propagation in bioengineering. So you can see this is a very vast field in terms of its um, impacts and areas, but also unknowns as well. So first of all, a wave, I'll just give you some examples before I show what I'm going to talk about. So this is also a relatively new field, but wind turbine is going offshore for obvious reasons because you don't have much space. Onshore left, there is also no impact on the visual or environmental aspects. So obviously, prefer to go offshore. The challenge is the cost is high. That's because we do not know a lot of features about waves and so on. So the first thing is that if I ask you what a wave is, you draw a sine profile line. So this is a wave. So you have a peak, you have a trough, but what we find is the waves that we see in ocean or water waves are typically like this. It's the first difference. So you have very sharp crest and flat trough. So they are by no means sine or cosine functions. So therefore, the classical linear or linearized or perturbation from linear wave theory is actually not applicable for bottom, which wind turbines. The first thing is this. The second thing is that what I was saying that you can have rogue waves, including something like this. You can have very sharp, deep kind of waves like this. And when this lands, there will be huge pressure on the platform of the wind turbine. And the third example is in terms of the wave breaking, for example, like I'll draw the wave breaking. This is first general nonlinear wave. So nonlinear wave. And these are closely connected to what is called the nonlinear Schrodinger equation. So the second one is we talked about slamming and rogue waves. And the third is wave breaking. So what happens is that if you have a wave like this, then slowly, as the wave amplitude increases, it becomes like this. And then at some point in time, what happens? That I'll draw it here, it goes like this actually. And then at this stage, it will actually, you can see this, if you look at the slope here, so this slope is almost vertical, 90 degrees, and tan of 90 degrees is infinite. So basically, you have a value of infinity here. But then, you have also seen, this can further proceed to a shape like this. So that means now you have a real difficulty. And what is that? Can anyone say? If you want to deal with problems like this, which will obviously happen when we're looking at offshore wind turbines, is we want to know the load, obviously. What's the first challenge? Can we represent that by some means? Have you heard of something called a function? Function, mathematical function, right? So all the calculations we do are based on functions, right? Like sine, cosine, exponential, and then you can do a lot of manipulations. A lot of things we do are represented by some function, right? And function is a graph. Like if you have an x-axis, if I give an x-axis like this, you give me a value of y-axis, right? So that's a function, right? But is this a function? So look what happens here now. So at this particular point, you have a value here, you have a value here. So this is not a graph anymore. And if that's the case, then you cannot represent it by any function. And that means you cannot do any calculation. So we are interested to know the velocity, we are interested to know the pressure and so on. So how can we deal with these sort of what we call not function but waves actually come up? So that's such a third challenge. These are some challenges I've seen. There's numerous amount of challenges. And a lot of the open questions in physics and mathematics are related to this. And now we are dealing with that sort of a difficulty to encounter and to solve for offshore wind turbines. So obviously, this is almost going to break, and eventually what happens is that this wave kind of breaks here. At this point, it's touching here, it's almost breaking. So this is at the verge of breaking, and then it breaks. Now, this is actually not necessary that it break like this. And in fact, very recently, people have found you can have waves like this actually. So I'm drawing some shapes. Waves like this can happen. And this is actually, as I said, this is sort of the wave, which is called the Stokes wave. And this is a Stokes wave of extreme height, meaning that given a certain flow head, the wave can actually achieve a certain height, and there's a bound to it. And also there's a bound to the slope. This has to be like this. And this was projected by, so has been proved for some places, which is basically irrotational. And there's been very recent proof in the last 5 to 7 years where you have vorticity or vortex. And you can see at this point you have a discontinuity. So we're facing a lot of challenges. And in fact, very recently we have shown that if you have rotational waves, meaning that if you have vorticity, then normally what we expect, if you have a water flowing like this, then the pressure increases as we go down, right? Hydrostatic increases, hydrodynamic also increases. But what we have found that there are situations where pressure can decrease. And in fact, we can have a pressure less than atmosphere. The very recent result we have found. So that is of concern now, because if you're going to design your offshore structure based on obviously some load that has to come from the pressure, and if the pressure is negative, that means you may have instability or destabilizing effect. That's also counterintuitive because we expect that pressure will increase. If it's hydrostatic, linearly increasing. Hydrodynamic, obviously there'll be additional pressure. Normally hydrodynamic pressure is maximum at the top and minimum at the bottom because of for particularly rotational water waves, but for rotational ones you can also have similar results. Okay. So, in fact, that is one of the reasons why divers can go deep down, because what happens is that the hydrostatic pressure increases linearly, but our body is made of 90% fluid, So the hydrostatic pressure inside and outside they get balanced. The dynamic pressure is maximum at the top. Its variation is different. So hydrodynamic pressure is at maximum at the top and actually decreases as you go down. So this is the hydrodynamic pressure part. That means if you go deep down, mostly the hydrostatic pressure which will actually balance the fluid pressure inside your body. And that's why you can actually divers actually can go down deep down. The hydrodynamic pressure is not pressure. So speaking about rotational and rotational water waves, so If you have rotational water waves, then you have vorticity, and then most of the linear water waves also use a theory called the potential theory. So potential theory basically means that given a fluid domain, the velocity can be transformed into or mapped into domain, a function called potential function phi. And if you take the gradient of the potential function, you get the velocity. So phi of x. So phi of x is del phi del x is your velocity u. Del phi del phi is your velocity. And obviously, it's fluid of the velocities and the pressure as you feel. So if this is the theory that is used actually for all calculations, then the fluid domain satisfies what is called the Laplace equation. So this is actually the potential equation. So let me just write it here. So the Laplace equation in 2D, basically this means that del 2 phi del x2 plus del 2 phi del y2 equals 0. So this is the del 2 phi del 2 del 2 phi del phi. So this is your Laplace approach. If you solve this, then you can solve the problem. But if you have vortices, and we know that there are vortices, like you have eddies, and that actually makes the flow irrotational and sorry, rotational, and this irrotational potential theory is invalid. So again, not that you have these problems, but also, first of all, there's no theory developed so far for large amplitude global nonlinear waves, and even the first existence of that was shown before. That people only thought that you have waves, then perturbation from the waves gives you small amplitude waves can be dealt with by the perturbation theory, and then you have wave breaking, and Stokes wave was known, of course, but large amplitude waves, so this one actually. But if you look at the seashore, typically you will see profiles like this. Short peaks and flat troughs. Next time you go near the seashore, try to observe. So you can have large amplitude waves which are stable enough. The existence of that only was not included. In fact, my advisor actually proved it, but the theory is fully not developed. Also, the wave breaking results were not known until 1998. So, not all waves will break, but which one is going to break will depend upon the initial condition where it starts. So, all these things are pretty difficult to handle. And on the top of that, I'm saying that potential theory is invalid. I'm saying that linear theory is invalid. And when you have current with the waves, so that means I have to can't probably see it on the back, right? Because I just want to keep these things because when I'm using it, maybe I'll refer to this. So what I'm doing is maybe I'm using this part of the board now. So essentially, you have a flow like this. So this is the bed or ocean bed or river bed, and your wave is propagating like this. But below this, you might have a shear flow like an underlying current. And this particular current interacts with the wave, and the wave current interaction actually will change something called a nonlinear dispersion relation. So what is dispersion now? So dispersion basically, so I've said potential theory is not valid, linear or in perturbation theory is an approximation. And then finally, I said that dispersion is nonlinear. This is exactly what Feynman was actually referring to. So nonlinear dispersion means different waves of different wavelengths or frequencies will propagate at different speeds. And what does it mean? That means that certain wavelengths of wave will actually arrive first compared to others. This is what you see again near the seashore. That you find that initially the shorter waves come first, if they propagate at a higher speed, and then you get the longer waves coming. Now, this is not the case for the acoustic waves because had it been the case, then hearing would have been very difficult for us. Because then, whatever we speak, this particular sound can be decomposed into a number of frequencies, obviously, by Fourier transform. You record the sound pressure in terms of the pressure in terms of your microphone, then do a Fourier, and this will get various frequencies. But these frequencies travel in air at a constant speed. They don't change. If they change according to the frequencies, then you will hear some sounds coming first as compared to others. So what I speak, you won't listen as exactly as I speak, but some of the things I've said would actually reach you after some of the things I've spoken later. So that's one of the things actually. So acoustic waves are linear. So is electromagnetic wave, light as well. That's why you see things as well in a sequential fashion. You don't see things that happen previously first and then things later. So, but in water waves, it's a problem. So you have nonlinear dispersion. And in fact, I was talking about solitons. Solitons are waves like this. So these are waves. They're not solitary waves, but you can have single waves which can propagate thousands of miles without getting dissipated, meaning without any damage. And like tsunami, for example. And that happens because that wave can propagate over thousands of miles without the energy getting dissipated. So these are called non-dispersive systems. So you have dispersive system, but you have non-dispersive. Sorry, pardon. The dispersive system, but non-dissipative system. So you have dissipative systems and dispersive systems. And if you see the Navier-Stokes term, you had a term U del U del X, which is the dispersion term. You had the term del to U del X2 associated with your viscosity. That is the dissipating term. So in general, in various physical phenomena, somewhere you find the dispersion dominates, somewhere you find the dissipation dominates. And even in a single problem, there are regions where one dominates the other. So the interaction between these two also is quite common. And in water waves, I was saying that this dispersion actually makes things very complicated because the dispersion law is nonlinear, and therefore, if you have waves, which are nonlinear waves, traveling, these actually lead to something called a nonlinear resonance. Okay. And what does it mean? It means that two frequencies will come, omega 1 and omega 2, they will interact and create a third frequency actually. And this is also true in nonlinear optics as well. So in water waves or in nonlinear optics, so we are concerned with nonlinear water waves, not optics, obviously. What happens is that if you have two frequencies, they combine to become a third frequency, which is not any of the two, or not just the sum or the average of the difference of the two. Because in a linear theory, if you take two frequencies and add the two frequencies, like sine omega 1 and sine omega 2, you might get omega 1 plus omega 2 divided by 2, or omega 1 minus omega 2 divided by 2, because this comes from your trigonometric expression. Sine A plus sine B. Sum it up, you get those frequencies. But in a nonlinear dispersion, you get a third frequency. So now think about a situation where the wave has been generated by the wind, which is called the pitch, and I have two frequencies interacting, which generates a third frequency, and this keeps on happening. That means the wave spectra that you get is actually quite nonlinear and will be changing as well. Now, this theory is also something not fully developed or known, and all we do in analysis is use some empirical spectrum. As I mentioned about the turbulent spectra in wind, you have also spectra in wave, like John Schwab spectra or Pearson postulate spectra. But these are empirical spectra from observation. You take some data, do a statistical analysis, and use it. But that is actually far from there. So there's so many challenges now open. So at least 10 problems I've told you. These are not trivial problems. So each of these problems will need a few years of a few thousand people to work to solve and solve. You know? So there's so many challenges, and clearly resolving these challenges and coming up with a proper engineering solution or design solution is obviously another further step in terms of that. So I think I have given you an introduction, but I think this was necessary to put everything in the context of what is going and where it is going. So let me now go back to the wind turbines in particular, keeping all these things in mind. By the way, for this afternoon's exam questions, I won't ask questions from the spot model because I don't think I will be able to cover everything. Yeah, I can ask you some questions, obviously, I can set some questions, but you won't have time to digest all these things by afternoon. So I'll leave this point. I'll ask questions based on classical onshore wind turbine, which has been covered in the last few days. So obviously, I said I've discussed all these things. The wave wind interaction. I mean, there are some papers, but there are not many actually. So these are all topical areas of research as well. But offshore, I mean, this is very important. People are building wind turbines now, actually offshore. They're going far offshore, deep offshore, and so therefore this needs to be addressed. So they are doing it in some way, but it's not fully understood or fully researched. So wave current interaction, dynamic analysis of floating wind turbines obviously is very important, as we have seen. That's actually the key thing because not much of change has happened in the structural dynamics. Not much change has happened in the classical control area in wind turbine. And obviously, we need new controllers to control offshore wind turbine. But first of all, we need to understand the system before we can design the controllers. Aerodynamics will not change much, and as it is. Of course, what will change is the wind-wave interaction, how the shear force transfer happens, and so on. And in this case, obviously, you have a very complex fluid structure interaction problem. And I will give some examples here of some of those. So wave current interaction is another area which has not been looked at. And only recently we have done some work. Even the commercial, obviously, I mean, in industry they don't have all the knowledge available to design all the things, but it's only recently these areas that are being. And wave travels on the current and affects obviously the frequency shift and shape modification in the spectrum, as I said. That's very important to consider. And the airy theory for computation of flow velocity and acceleration is not valid because it's based on the potential. So the focus of today's lecture mainly is, as I said, the structural dynamics is there. Controllers, we know. Aerodynamics, we have obviously learned something. We can calculate the loads, DEM. We can calculate the structural dynamics equations. We can solve those. We can do all those things. So my focus here is mainly going to be on the load side. That's what's going to change. The joint load, the wind-wave interaction, how the spectra is going to be impacted, wave current interaction, and then we'll take an example, which is a spark-type floating wind turbine model. I'll give you the crux of the model, so you can follow the similar approach as we looked at yesterday, and write the equations and solve for it as well. So the aim today is to give you some information so that you can reproduce this and get a similar kind of following this. So I'm not going to discuss this further because I'm already given the introduction of the complex environmental load is subjected to. The safety of this kind of systems are of primary concern because I've told you about the environmental cost if some of these kind of get damaged and the recovery required from the sea. In fact, it happened actually in North Sea, one wind turbine, I think it was for the Vestas, toppled and it was a huge impact. Obviously, it was had to retreat and so on. And particularly when it becomes very difficult for offshore wind turbines. And also, because of various motions and the platform now being actually not a fixed platform, you have degrees of freedom at the platform, which actually induces various complex motion of the blade and power, and therefore you need the pitch and the generator controllers to be designed to take into account all these phenomena. There's lack of literature on modeling wave and current loads. And again, another area is non-linear mooring dynamics for floating offshore. And again, that's an area where people have done linearized analysis, but you can do more complicated analysis, and it's required for wind turbines as well. So I'll also give you some information for design mooring cables and what are the softwares out there, including one software we have developed, which is open source and available online for downloading from GitHub. But also we have a website of ours as well. And it's a licensed software, but it has an open license. So if you want that code or help, you can contact us. But I'll give you the details of those as well. So now you understand about the spectrum, which gives the variation of the energy of a stochastic process over various frequency ranges. Okay? So we know we have seen the wind spectra, which is like a common spectra called, and in wave it is called like non-stop spectrum. And the spectra basically gives you, so this is the y-axis, gives you the amplitude as a function of the frequency omega, and then you have certain parameters which depends on the water surface elevation and so on. And you can notice from here that obviously it's a function of frequency, which will vary with the frequency, and you can plot it. You have parameters like G, and there's another parameter called alpha. This is important because in this particular case, what we can do is you can see that the alpha is a function of U10, meaning that wind velocity at 10-meter height. So obviously, this is one way to account for the wind on the wave spectrum, though not fully, in the sense that the wind actually generates the wave, because when the wind blows, obviously that actually excites the surface and the waves are generated and slowly they build up. So that's how the waves are formed. So this wind velocity will affect the formation of the wave spectrum. I mean, it will affect in a more nonlinear way because we have not accounted for the shear transfer between the wind and wave and so on. But in a simple way, it does take into account wind and wave function. And so once you have the spectrum, you can take an inverse Fourier transform and generate the wave loading if you want. And then you can use this U10 also to generate your wave loading. Sorry, wind loading. So that means your wind and wave loading are correlated now by using the same U0 value. And the total wind force acting on an offshore wind turbine again can be obtained by calculating the wind pressure acting on the blade or on the tower, or for the spar it has to be the hydrodynamic load actually, and then apply the shape function, which is the mode shape, and you get the modal load as we did in the previous. So in the structural dynamic model, I showed you the generalized load, which included the distributed force and the mode shapes actually came from what you want, all of that. And then obviously from the pressure, so this is the wave pressure which is acting. Now this is also the when I say this is the wind force acting, you can also have a similar kind of wave force as well. Now here we have determined this P, or denoted this by P, but it could be wind or wave, and the wave force which acts on a certain column, because if you see the wind is supported either on a monopile with a substructure, or it's supported on the spar like floating wind turbines. And I'll show you a diagram very soon. But you need to calculate the force acting on the surface of that particular structure. And you apply the pressure, and then you have to integrate over the surface. And in this case, the wave force is given by what is called the uh, Morrison's equation. And what Morrison's equation does is basically takes the velocity profile and then using that calculate pressure. So you can see that here we have actually something like a drag force, the first term over here. The second term is coming from something like the Kn times Kz, which is the acceleration, and Kn is dependent on Tn and rho squared, where d is the equivalent diameter, and you have the velocity and the acceleration given by this expression. And omega squared is the frequency, and k is the wave number of the wave that we are looking at. So here you can see we are using this velocity and acceleration term, which actually come from the solution of this equation. So again, I'll show the solutions. I won't go into the detail of all the mathematical calculations to find this out. But when we analyze the wave loading on the wind turbine, but this is essentially how we're talking about how to connect the wind to the wave. So it's through U10 you can connect the two. So now you take the U10 and use that in your wind profile. Because if you remember, your log or power law profile will require wind velocity at a certain height. And so you use that U10 and then use that value to get your profile for the log or power law and generate the wind profile. That's how it should be for the coordinate. And the wind speed at 10 meters, U10, and the significant wave height from the Jones-Swap spectra, HS. So a wave obviously will have a wave height. So that is one characteristic. The other one is the wavelength, or you can write it as a wave number, because waves have both space and time signature. Unlike a single signal, the wave is propagating in space, but also in time. So you can represent it by x minus ct, where c is the velocity of the wave. At a particular point, x and at a time t. So that's coupled by this x minus ct. So the wave function is always represented as a function of x minus ct. And in this case, obviously, we are showing that how the variance of the spectra can be related to this sigma square value in the first moment, lambda 0. And the wave is obviously having a height of hs, and there are different frequencies obviously are there. So that's represented in this spectra for different values of omega. And then once you know the spectra, you take the spectral amplitude and then use this to generate your time series by using a trigonometric polynomial. You can see that we take this value of S eta eta, which is the Moore spectrum value, and then we use a sine and cosine term with this, and then we sum it up for various frequencies to get that corresponding time series. Now, this is for a particular time, obviously, and you can do that for various locations in space, because if you look at the spectra is see that this is actually your function of z and t. So all these are functions of z and t. So obviously, the spectra function of frequency. If you're looking at this particular spectrum at a particular location, then obviously from there, what you need to do is then apply the load, and do that. Obviously, you're using this eta t, which is generated from your spectrum, but the function z is the spatial function. So eventually, you get a function of space and time. So the spectra is giving you the function of time, which is the time series which we have now generated. So this is the xt. Xt is essentially actually your eta t, and the space variation is given by this. So really what you can see here, the way this has been solved is we have actually decoupled space and time. It's the product of the space and the time. And in partial differential equation, it's called separation of variables. So separate the space and time and get the solution as a product of Okay, so now we move into the wave current interaction model. And here, as I showed, that this is the wave traveling on this shear flow. So based on your basic fluid mechanics, you know that this is a laminar shear flow, and this is actually the wave which is generated at the top. Normally for laminar flow, you don't see this happen. But we have a wave here, and this is now interacting with this current. And obviously, because of the nonlinear dispersion and the wave traveling on current, there is a frequency shift, is a Doppler effect that modifies the spectrum. So, because of this presence of this, there is a shift in the frequency. And the resulting pressure and velocity fields are given by this. So, this is the uz, which is your beam field here, and this is the wave on the top of the field here. So, obviously, this is again a function of x and z and t, because now you have a two-dimensional domain. Similarly, v can be represented by this expression here, and p is given by this expression here, to the pressure. So you can see we have presented everything in terms of sine and cosine, which is not correct, obviously, we know now. And also, as I said, we have used this kx minus omega t. So omega is the frequency, k is the wave number. Okay. So with this interaction, we will now be able to look at the impact of the wave and the current and calculate eventually the velocity and the pressure. So that's what is going to be applied on the structure. Do you understand the relation between this wave number and frequency, the wave speed? Yes, maybe not all of you. Okay, we'll come back to that later. But let me just go through it and then we'll have a discussion. So what we assume is the free surface is given by this. Now, what is interesting is that obviously this eta is the free surface, and we are getting the power spectrum of the free surface. So once we know the free surface, the rest is actually solved, because then we get the rest of the flow parameters as a function of what is happening at the surface. So this is actually called a nonlinear free boundary problem. And the free boundary is actually an unknown. So normally in finite differencing or finite element, what we do is we want to solve a problem and we take a domain, and obviously the boundary is known. But this is a problem which is actually difficult because the solution for what we want to get over the domain is unknown as well, because the top surface is also a solution of the problem. The boundary is also a solution of the problem. So this is a problem typically faced in fluid structure interaction problems or nonlinear boundary problem. And then the solutions are obtained as this is your sort of your potential flow equivalent here, and then U, W, and P are given by these three expressions here. And note again here, considering everything as sine and cosine term, and obviously the depth variation is given by this hyperbolic function in terms of z, and the amplitude here has actually a shift now from frequency omega with a value of u0 times k, where u0 is the velocity and k is the wave number. So you can see that now the amplitude is actually being affected because of the presence of this u0 of the current. So what we've assumed is that u0 is the current which is propagating under the wave, and that actually impacts the response of the fluid. So here u0 is the current velocity at z equal to 0. So z equal to 0 is at the top surface. So obviously the profile is nonlinear, but u0 is the value at the top. And then based on this, we get a modified dispersion equation. So this tells you what is the relation between the speed of propagation of a wave with frequency omega or wave number. And more uniform current, that is, if you assume that the current is not nonlinear in profile but uniform, you get the result like this. And then there are some bounds available on the wave height and current velocity. So, so on the theoretical analysis of all these things, you can actually look at some of these papers. They're very mathematical, but if you're interested, you can look at that. But this is where the nonlinear interaction comes in. So you can also look into the stochastic interaction because we're now looking into the spectra. We want to modify, the spectra that I showed you in terms of the existing current and the current velocity. And a simple model for modifying the wave spectra based on uniform current. So as I said, the current is nonlinear, but let's say you have a uniform current. The code says that you can have three different kinds of current. One is uniform current like this. One is a linear shear. So one is uniform current like this. Other one is a linear shear you can have like this, or you can have something like a profile like this, which is developed like shear flow. And this is a offshore code by DNV. In this case, the spectra is modified by using the velocity of the uniform current velocity. And this then could be used for analysis of the loads. Similarly, you can look at the wave current interaction using the Johnson spectrum, for example. And in this case, you have the significant height, the period like this, Hs and Ct, which characterizes the spectrum. These are the scaling and the peak shape parameters. And on a favorable current, you can then again modify this expression. You also have something called an adverse current. That means if the flow is in one direction and the current will be in the opposite direction, that has to be also accounted for. That's actually a critical case. What we found was the responses and the loads and the forces in the mooring cables are significantly increased if there is an adverse current. That may be a critical. And favorable is when the waves are propagating the same direction as the current. So two cases can happen. And in this case, we again compute the wave elevation by using this sine cosine function, and the fluid velocities and accelerations are obtained by using this expression, very similar to what we had previously, except that, yeah, but yeah, the same way, and the amplitudes are modified by the term omega minus E0k. So in this case, obviously, you can be positive or negative. That will actually change your overall. And this is an example where we have a spectra without interaction and with current interaction. So you can see that here we have assumed the uniform favorable current of 1 meter per second. Okay, so I think we will move into the spark type floating offshore wind turbines. I don't know whether is there a break for 5 minutes or so? in terms of with the nonlinear wave theory, but obviously if we're dealing with offshore wind turbines, these obviously are going to appear, and we don't have enough time to go through the details of it, but because that's the direction where the wind turbines are going towards, I thought anyway it's good overview. So you have some references which you can look at, and we'll go through some of the things in linear wave theory in more detail in the following slides. So now obviously we want to see what is the result of this. So clearly you can see that if I consider the cable response and take the wave without the current, then there is a significant difference. You know, the red one, sorry, the black one is without any current, and two graphs, blue and red shows the red with current. So obviously for offshore wind turbines, the current is very important to consider. And not only that, you can also see that the red and the blue curves, maybe not so much in the maximum value, but there is a bit less as well. And the variance, but they're also different. So that means even with the interaction, so without the current, obviously it's significantly different. Even with the current, if you not take the interaction, then the response is also different. And this is for one case, but obviously it shows that you can have a difference in the response that might actually impact the design. Don't know very well in detail how it might affect, but more studies are necessary. That's actually what this shows. So this is a snapshot or a highlight of the region. Here we see that this is a black curve, and then without the interaction is the red curve, and with interaction we're getting the blue curve. So some of the topics, as I said, the modeling of the spar floating offshore wind turbine is interesting. Nonlinear wave dynamics, sorry, mooring dynamics and the coupling is also important area. Already seen the effect of the wave current. They started with actually. It should have been done later, but I wanted to emphasize the importance of this. So in terms of the mooring cables, I mean, there's been a work done, and there are two papers which you can actually follow. And the design of the mooring system and the response based on the model are pretty well discussed and given in these papers. You can follow those relatively easily. And one was to look at the control of the vibration with multiple two-month damper. The other one was more focused on the effect of the wave current interaction. And the spark type model was based on a model developed with a former student of mine, and the nonlinear dynamic model for cable was taken from a group in MIT who have developed a mooring dynamics code for moving. So this is now our model. And let me discuss this a little bit more in detail. Oh, sorry, I should have mentioned to you about the wave and the wave number and the wave frequency actually. So we'll just stop here for a moment. I'll come back to this. Let me explain you what we mean by so obviously, let's say we consider a wave which is propagating like this, space and time. So we were representing any particular function like the velocity u by kx minus omega t, or we could say also x minus ct, I said, where c is the velocity of propagation of the wave. So the velocity of propagation of the wave and the velocity of the fluid particles, they're very different. The fluid particles are propagating like this. So at any point, you have u and v velocities. So this is u and At the crest, you don't have the v velocity, but you have a velocity u. But that's actually not the wave speed. The wave speed is the speed at which the wave front is propagated, meaning that this part here, at this point in time, say space as well, then this is our x equals 0. And when the wave propagates, this is going to be like at this point here, but as time goes on, this goes down and reaches a minimum, and then it comes up again. So this period actually is the wave period. So the wave propagation front, which is governed by how the front is, or the amplitude of the envelope is going up and down, determining the wave speed. Whereas the velocity of the particle, if here is u, or any intermediate particle be u and v. Here, v is 0 at the top. Similarly, at the wave trough, you have v equal to 0. No particle velocity, because at that point, particle is at its minimum, and then it will go up again. Okay? So, the difference between the wave speed and the particle speed, obviously. And wave number gives you the number of waves per unit length. Okay? That is the wave number. So, if k is the wave number, so you have k waves in 1 or unit length, 1 meter. So that means one wave will be 1 over k length. That means this is actually the wavelength, right? So inverse of k is actually your wavelength by lambda. And in terms of the frequency, obviously we have frequency gives you the number of oscillations per unit time. Okay? So obviously this is frequency is number of oscillations per unit time, and that means one particular oscillation will happen in 1 over f time. So that means that is actually your period, right? So and this frequency is in hertz, number of oscillations. You can convert this to frequency in radian per second by multiplying it by 2 pi. So frequency omega is 2 pi. Okay. So now we can get the relation between the time period and omega, and here we have the relation between the wave length and wave number. The only part now we are left with is to connect these two. So this is happening in a spatial domain in length. This is happening in time domain. But in case of the wave, we see that this is actually changing in space, but also propagating in time. So time and space are coupled together by something like this. We can write this as either kx minus omega t, or you can divide through it by k, and you have x minus, so you can write this also as x minus omega over k times t. Take the k out. So effectively, this omega over k is acting like your velocity c. So basically, if you want to couple the time and space, this is a spatial position x. We can also get the same effect if we propagate the speed in t and then over time t. So that means if I move that by a value of c minus t times t, I'll get the same effect as x. Okay, so that's why we're using this, and this is actually something like a wave speed. And the wave speed actually connects the wave length and your frequency of the wave. Okay? So these are the relations between the wavelength, wave number, frequency, time period, and the velocity. They're connected actually, right? And And if you take the wave length, lambda, and divide it by the wave speed, what you get is basically the wave period. Or if you take the wave period and multiply it by the wave velocity, this wave period is the amount of time one particular wave takes to travel. So if you take multiply it by the wave speed, basically, then you get what is uh, uh, the distance it will travel per unit length effectively, and that is nothing but your wave number. So that is the relation. So that is how they are connected to each other. So let's come back to the uh, wind turbine example. And this is the same wind turbine with the three coordinates of the blades, the nacelle. This is the tower. Obviously, the degrees of freedom, if we consider 3 plus 1, that is fine. The only thing now is what's going to happen is the platform is moving here. So the platform degrees of freedom will have to be added to our system equation. So in general, you will have 6 degrees of freedom. So so you have a sway, you have a surge, you have a heave motion. So heave is the vertical motion. Sway is this motion. Surge is the out of plane motion in this case. Then you have 3 rotations, which is basically the yaw, which is the vertical axis, the roll, and obviously uh, the pitch. So pitch, roll, and yaw are the 3 rotational degrees of freedom, and wave, surge, and heave are the 3 translation degrees of freedom. So 6 degrees of freedom. But if you consider this in 2D, then you can move in this direction, and so you have the heave and you have the sway in this direction, or actually depends on how you call sway and surge, one of the two. And then in terms of the rotational degrees of freedom, the only one you can have is basically the pitching motion, right? You don't have the yaw or you don't have the roll. And then it's connected to this cylinder, which is a spar, which is an extended cylinder. So this is really the support structure, and they are eventually connected to the cable, mooring cable, which is lying on the seabed. And let me tell you that seabed interaction also is very nonlinear. You can have reflection of wave coming from the cable and connecting and affecting the spar as well. But spar is preferred because you can see that it's a very narrow structure, so the water plane area is minimal, the load is going to be minimal. Also, because it is extended, so it gives a stability to the overall system. That is why for deep offshore wind turbines, like 50, 60 meter water depth, spar is actually preferred. So the top part you can analyze the way we have done, but now we have to add the degrees of freedom and change the corresponding, like 3 degrees of freedom here, and change the corresponding potential and kinetic energy terms, as we did, and then go for a stationary Lagrange population to obtain the equations of motion. There will be some additional equations of motion. And in terms of the loading, we've already discussed you have to take the wave and current loading. And the cables, in a simple way, can be modeled as a spring. So first of all, we can take the cable, take the lateral stiffness, and replace it by a spring, so that as if it's actually applying a spring force to it. Now, it's also nonlinear, so we can do a full analysis, and that's what we've done in one of our papers later. But we can do a simple analysis with a quasi-static spring here. The intention of the cable here is not to apply the load really, but just to keep the whole thing in position. So it's not actually tension cable, just anchored here. There's no force or retention given to this. Just this is making sure that the whole thing actually doesn't drift away from its position.
So what are the boundary conditions related to the
What the-
bottom? Yeah, boundary conditions
related to
model analysis of the whole system. You want
well for the system, obviously you can see that here we are taking the 3, 4, 5 and then centimeter 2. So these are the degrees of freedom. So you have the ordinary differential equation. So it's not a PDE. So you don't have a boundary condition. Yes, for boundary conditions, you need the PDE. So because it's a set of OD, you only need the initial condition.
Looks like it's 3-3.
Well, we'll come to that because there's also we'll have to talk about hydrostatic stability and hydrodynamic stability as well. So it is not completely in that sense because what is happening is that the buoyancy is uh, statically supporting it constantly. So there is a spring coming from the buoyancy as well. So effectively, there's a spring connected here as if which is supporting it. Also lateral stiffness and rotating stiffness of the water surrounding. So it's not 50 in the sense because you have fluid medium here. And the two ways to model that, either you couple it with your potential theory, the Laplace equation, or take the full Euler equation, and then you will need boundary conditions actually. Because then what is the boundary condition on this place? What will happen is you can assume this part will be implicit, and then there'll be some pressure boundary condition here. Maybe some viscosity is also there. So you'll have a normal boundary condition and tangential condition as well. So there'll be kinematic boundary condition to ensure, but also there'll be a dynamic boundary condition as well, because you know that on the surface here you have atmospheric pressure, so that is the dynamic boundary condition, leads to particle depression. But here you don't have the pressure, so that gives you the dynamic boundary. So you have kinematic and dynamic boundary condition. The kinematic boundary condition is that the velocity here has to be 0 or equal to the velocity of this surface. That's the kinematic. But then you're doing the full analysis of the structure with the fluid domain, which is actually the portion. You then have an ODE system coupled to a set of PDEs. And then you also have the cables, which are also PDEs as well. Very complicated. But yeah, you can these are things people are working on. You can do that as well. And then you have to talk about the boundary condition in the C base as well, because this is a flexible foundation. So it's an elastic foundation. So you can model this as a beam on plastic foundation. But also non-linear, because what will happen is there'll be sometimes loss of contact. So then that will actually lead to behavior like stick speed and so on. That will also induce some kind of non-linear waves, which will propagate back. So, but in a simple way, if you just don't consider the effect of the fluid on the structure of the fluid structure problem, then because then you have to solve the PDs, of course. Then what you simply do is take the ODs, as I've said, and then take the mooring cable with an equivalent spring, and then you have a set of ODs to solve. So, okay, so the 3D motion of the platform, the mooring dynamics, elastic deformation of the blades and tower, rigid body motion of the blade and tower, and edge-wise vibration of the wind turbine. Retained again, and you can do the analysis as we did yesterday. I showed you how to write the equation. So this is now the system, with all the details with wake and turbulence, jet, turbulent wind, tidal surge, extreme waves, currents, and tides. You can also have ice sheets as well, hydroelasticity, right, of that, do that. And it is actually there in some of the options. So the challenges we've already discussed there quite in detail. And not everything can be done fully, as we have appreciated. But something can be done, and based on that, what we can do is obviously write the equations of motion, just now as I said, and this is the schematic diagram with the degrees of freedom. So this answers your question actually, in terms of how do we actually deal with this. You can see there's a lateral spring stiffness, and there's a rotational stiffness, and a vertical spring stiffness. So first of all, we have to, and the details of this is available in this paper. And the expressions for these springs are also derived based on, as I said, the interaction of the fluid with the structure. So this is 7-degree of freedom system, a 2D model taking first modes of the blade and tower side mode and then also the surge degree of freedom and the role the platform. So, so if you just look at the spar here, then we effectively have a center of gravity, and then the meta center will ensure that this is stable based on the hydrodynamic analysis, and the dimension of this is decided based on that. And then obviously you will also have hydrodynamic loads, and you have to analyze the whole thing to ensure the stability. And you can see the spring here is giving a force which is T0 on two sides of this. And this is only in action if the whole thing is driven. Otherwise, this is actually not active. Because if it's T0 on both sides, then it's going to be nullified. The only situation when this is drifting, then one will become T0 plus delta T, other one T0 minus delta T. It will try to bring it back to the original position. So some more definitions here which you can find in this paper. And so this is what we define as sway. Okay. We're considering the sway motion, and the heave is in the vertical direction. And again, the same azimuthal position, Euler-Lagrange equation, displacements as we have considered previously. Now, obviously, because the nacelle is not just laterally moving, but there is also a tilt because of the tilting of the platform. So that is accounted for in this additional term here. That's what is coming from the offshore. Which was not there for the onshore wind turbine. Then, based on the generalized coordinate, you again find the absolute velocity vector, with the INJ, because I told you yesterday how to take the effect in terms of room dynamics and differentiate I and J and get the corresponding J and I. And then take the total kinetic and potential energy of the beam, the nacelle, the platform, both the inertial mass and the mass ms. And this is the rotational inertia here because the platform is rotating, so that needs to be added now. Again, the stiffness term is coming from all the conventional terms, but now you have the additional terms for the platform. And with this, now we can actually use the Euler-Lagrange equation to write the equation. And in terms of loading, you of course have the wind loading, but now you also have the coupled loading of the wind and wave as well. And this is what we've already discussed before. So if we do this and calculate all the loads and analyze, first of all, we do the hydrostatic analysis and find the initial depth of the top of paper below the mean water level. Simple Archimedes principle. Buoyancy, make sure this is stable. This is actually the distance between buoyancy and the center of gravity. And then, obviously, we want to find out the particle and the roll restoring coefficient based on the springs that we have seen. So we do the basic fluid, not even dynamics, actually statics. Get those. The loads obviously will be hydrodynamic loads coming from the Morrison equation I showed this morning. And then the two things which come in, which are called the hydrodynamic added mass and hydrodynamic added damping, needs to be added to your system. And this is added to the degrees of the freedom of the spar actually. And finally, this is actually a summary of all the loads we have, the hydrodynamic Morrison load, inertial force from the fluid particles. You can see it's proportional to the acceleration term here. The inertial forces from the fluid particle, the particle one, you get the acceleration term here. The viscous drag forces, that gives you the square term, you see Q dot, and then you have this Q and QG. So this Q is that the generalized coordinate. So a projection of this on Qn will give you the square term, so it's the drag force. And similarly, you have also the vertical drag force as well. And then our net normal velocity given by this expression here. And if you take all this into account, eventually you get the question as exactly in a similar way as we did yesterday. And finally, the mooring cable. As I said, you can do a full analysis with PDEs. We've done that. And you can look at a website called www.openmode.org, which is, maybe I'll have a look, I'll show you, which is our website for our code for open mode, which actually solves the partial differential equation for the table and the wind turbine. And also the codes are available freely on GitHub, so open source code we have developed. You can try it out and you can modify it accordingly if you want. And if you have any problem, you can contact me or student of mine to get together. But instead of going into all these details, if you have to design it in a simple way, you can use the horizontal stiffness and vertical stiffness. The expressions are given here. This is actually the roll stiffness here. And I think this title is missing here. Yeah. So there should be a roll stiffness here. This is the rotational stiffness. Just a small edit here. So if the stiffness term is horizontal, vertical, this is the roll stiffness. Is roll. And then this fourth one is the horizontal. This is the vertical. This is the spring stiffness corresponding to roll. And oh, this is okay, I'll check this one and let you know. I think this is also something. Okay, there should be a term K HP. Yeah, this is the one. The only term missing here is the roll stiffness. Just to make a note of that. So these are given in terms of all the dimension and parameters of the table, and using this you can find the stiffness, and the whole problem that is simplified just as springs connected to this. And finally, you get the equations of motion like this. And again, as we saw yesterday, you have mass, damping, and stiffness metrics, which are time varying. And you also have the coupling, inertial coupling, the coupling in damping and stiffness. And also, as we saw yesterday, we didn't assume any damping, remember? And we got this negative damping terms appearing because of the coupling between the tower and the plate. You'll have similar terms here as well. But on the top of that, you'll also have nonlinear hydrodynamic terms leading to these things. But anyway, this is the time varying system we have. And then the surface elevation is presented by this expression over here. And again, this is what we have seen. We get the velocity and the acceleration terms, and this is based on the linear potential theory. So solving that linear equation, potential equation, you get the solution. And they're also like, this is in y and this is in z, so in the two directions. Space and the time and space is also decoupled. You can see that the function of time here. The particle variation is decoupled from the variation of time. And these are some results. So these are some simulated wave velocities and acceleration from the model we have. And if you use those, you can get the results and analyze it. You can see that these are the responses we have. And a Fourier amplitude shows that this is actually, there is actually, this is the tower frequency, and this is actually the corresponding low frequency. And therefore, you can use various control strategies to suppress it, but this gives you the response. You can also see that actually, interestingly, that this is the blade response. Obviously, you have the blade response, blade frequencies here, effect of some amount of turbulence and the effect of waves. But if you look at the this is the edgewise, one is the edgewise motion of the blade, and this is BG, which is the spar heap actually. Okay. So this is the spar heap. I think there is this edgewise shouldn't be there. This edgewise is not there. This is spar heap. So you can see the spar heap is actually more or less sinusoidal, and it is a long period. So you can see the peak is about maybe 15 seconds here. The next peak is around 45 seconds here. So 30 seconds. So you can see that that the offshore floating turbine has a very long period motion. So half a minute it takes to go from one side to another. And that is actually a big challenge to control this. There's no method which can do it properly as of yet. Again, an open problem. But this is something spectacular. Half a minute period of transition. And finally, I mean, I mentioned to you, so you can look at this wind energy paper. We have done a full interaction analysis with floating offshore wind turbines, and the cables have been modeled by nonlinear analysis. And we used our open move code, our code, and also used the MIT code, which is the move code. Now, move actually uses a long mass model. So, in fact, ours is better than what the MIT developed move code is. Ours is a continuum model. Therefore, they cannot account for the current limit. The MIT code cannot be used for current interaction, whereas we can do that. And these are some results, of the power side and spar and so on. You can see the linearized model and what's the linear model, non-linear model, how they're actually changing. In some cases, there's not much of difference. So when I say linearized, quasi-static, and non-linear model, this is the mooring model we're talking about. And but in some cases, you can see there's a significant difference in the linearized and quasi-static model and the full non-linear model. So particularly in the spar particle displacement, you have a significant. There is a significant offset which is captured by non-linear. And we don't have any current here, U is 0. Again, you can see that there's. So it depends on the situation anyway. So I think we'll stop here. I did take a few minutes more, but we started a few minutes late today. So I hope I confused. So any questions so far? I know that this is a lot of material I've actually squeezed in for an hour half of lecture, but I think if you go through the details, the papers I've given, you will be able to find the detailed information. They're very, very well elaborated. So you can follow our papers and produce the results for all this. So probably I'll show you two websites. One is the Intel one, and maybe I'll do it in the afternoon because we'll have a session of interaction. Or open Moorsoft website, Envel's website, which is the Colorado National Renewable Energy website. And then I'll give you a couple of things like the Gearbox material in a PDF form, and then a small Excel sheet to show how you can model the tower with hybrid concrete and steel. Which elements are just taken a very simple 2 element. You can use that to develop the